You might be asking, we haven't done a whole lot of math. We've done a bunch of geometry, but haven't done much math. And I would say guilty as charged, but I will rectify that situation right now. Can you really do quantifiable math on these? And the answer is yes. And the nice thing about geometric optics, which is the subject of this chapter, is that you can do things both geometrically and mathematically, and you can use the one to check the other. So I would strongly encourage you, as you're working through problems, if you're having a hard time visualizing, if the math doesn't seem like it's working out right, draw a ray diagram. Put the object, put the image, figure out about what size it should be based on the ray diagram, and that'll help a lot. Okay, here is a derivation. I'm just going to sketch the derivation to show you that there really is a mathematical basis behind this. We're going to derive the mirror and the magnification equations, but I'm not going to expect you to know the derivation, but I think each of you should be able to follow the derivation so that you can see that there's actually a real sound basis behind these equations. So if we look at a concave mirror, so that's a concave, and we place an object at some distance from the mirror. In this particular case, the focal point is here. The center of curvature would be about right here. And so this object would be outside of the center of curvature. So the image, as we talked about before, we did a ray diagram for this one, is going to be real, inverted, and reduced. So here's that image. So we're going to define h naught as the height of the object. So now we'll be able to be more quantitative about whether it's magnified or not. We'll have an actual number, h naught, for the height of the object. And we'll have a number, hi, for the height of the image. If the image is bigger than the object, hi is bigger than h naught, then we'll say it's magnified. Or that is if the absolute value of hi is positive. So this is greater than h naught. This h naught will be a positive number because it's above the axis. This hi is going to be a negative number because it's below the axis for this particular case. The other word that we use for below the axis is inverted, right? Okay, so that's the conventions there. D naught, in fact, we're defining a lot of, this is a derivation, but it's also a definition of all the parameters you're going to be using. D naught, and so this is important. D naught is the distance from the object to the mirror. That's called the object distance. Di is the image distance. All right, that's the distance between the image and the mirror. All right, let's see if we can do a little bit of geometry. Because this red ray that comes and hits the mirror symmetrically right on the principal axis and reflects back off, because of the law of reflection, the angle of incidence, this angle, must equal the angle of reflection. Those two angles have to be the same. Well, you can use similar triangles to do the geometry here. How so? This red triangle is similar to this, I don't know, it looks like a green or blue triangle here. If you look at the side opposite this angle, I'm going to look at the side adjacent to this angle, and that side adjacent to this angle is this distance here in that triangle. That's D naught. So there's a side adjacent for that red triangle. Here's the side opposite to that angle, that's h naught. So we're essentially taking the side adjacent over the side opposite, which is the cotangent, actually, if you want to know, of that angle. But you can also look at that with this bluish colored triangle. The side adjacent for this blue colored triangle is the distance between here and here. Well, that's d sub I. The side opposite is minus h sub I. Remembering that h sub I itself is a negative number, then we're going to put a minus sign in here in front of h sub I, so this quantity in the denominator will be positive. Then from B, from this diagram here, we're going to look at another ray. And this one is a time-reversed paraxial ray, starting from the tip of the object, passing through the focal point, hitting the mirror, and then coming off as a paraxial ray. Same object, same image, but looking at similar triangles. Now this is just two intersecting lines, this red line intersecting with the principal axis. So this angle here has to be the same as this angle here. And those are not necessarily the same as the angles we talked about before. So if we look in this case at the side adjacent to this angle, that's d naught minus f. This total distance from here to here is d naught. If we subtract f off, then we get d naught minus f. So that's this beast right here. The side adjacent over the hypotenuse, which is h naught. And then we're going to look at this triangle. The side adjacent to this angle is this line here, and that's f, over the hypotenuse, which is minus h sub I. Then the rest is just algebra. Putting these two equations together, I'm going to divide the equation B by equation A. So here's B, d naught minus f over h naught. A is d naught over h naught. Then B is f over minus hi, that's here, over A, which is di over minus hi. Then a bunch of amazing cancellations happen. The minus hi's cancel, the ho's cancel over here. We get d naught minus f over d naught is f over di. And then I can divide both sides through by f, simplify. This d naught over d naught becomes 1, but I'm dividing by f, so it'll be 1 over f. I've divided this term by f, and it's negative on the left side of the equation. It'll become a positive on the right side. And then we've divided this term by f, which gives us this term. So this is the mirror equation. And the magnification comes simply also as well. The magnification is defined as, like we talked about before, it's the image height divided by the object height. So that if the image height is greater than the object height, the magnification will be greater than 1. So that's the definition of magnification, hi over h naught. And from this equation, we can actually solve for hi over h naught. And how do we do it? Let's multiply both sides of this equation by hi and divide both sides of this equation by d naught. That'll give us hi over h naught equals minus di over d naught, which is this relationship here. So, bottom line, it's a lot of math, is this concept. The mirror equation. And the magnification equation. And the conditions for real, virtual, upright, inverted, and enlarged and reduced. All right. F is the focal length. We did the derivation for a concave mirror, where f is a positive number. But this equation also applies for convex mirrors, where f is a negative number. That's what I said before, that if we define f as a negative number for a convex lens, a convex mirror, then the equations work out more simply. So F is positive for a concave mirror, F is negative for a convex mirror. No big deal. The object distance. If the image is real, which it will be for almost every single case that we talk about well, it will be true for all the homework cases. There will be one case in the lab where F is actually, where the object is virtual object. And we'll work through that case in the lab. But for almost all cases, for the homework, etc., the object distances will always be positive numbers. The objects will be real objects, not virtual objects. Now, images, we will get all different kinds of images, both real and virtual. If the image is real, then DI is a positive number. If the image is virtual, then DI will turn out to be a negative number. And sometimes you can just let the math tell you what DI is going to be. If you have, for example, if you have the object distance and the focal length, you can solve this equation for DI. And once you have a value for DI, if it's positive, you know that the image is going to be real. If it's negative, the image is virtual. So that's yet another way of getting in, well, that's the mathematical way for finding out about real versus virtual. Object height, well, we will just consider h naught to be greater than 0, so that object is going to be above the axis. Now, the image height could either be positive for an upright image, or in the case of the derivation that we talked about just in the last slide, here hi was below the axis. It was an inverted image, and h naught was less than 0. It's a negative number. Then finally, the magnification. If the absolute value of the magnification is greater than 1, that means the image is enlarged. And if m is less than the magnitude, the absolute value of m is less than 1, that's a reduced image. And then if its absolute value is equal to 1, it's unmagnified. But noting that the magnification is hi over h naught. H naught will always be a positive number. Hi could be a negative number. So that was the case in the video where I made a mistake and I said the magnification is 1. Well, it's actually minus 1 because hi was a negative number, and it was hi was equal to the negative of h naught. And so minus h naught over h naught gives a minus 1. So that's the way the magnification works. Let's do a couple of examples so you see how to plug these equations in. An object is placed in front of a concave mirror. The focal length of the mirror is 12 centimeters. So that tells you some information. If the focal length is 12 centimeters, what kind of a mirror is it? Concave or convex? Concave. So it's going to be a concave mirror. In fact, we've already told that. We've been told that. All right. If the object is located 8 centimeters from the mirror, what is the image distance? So you say, well, hang on. The focal length is 12. So here's my concave mirror. And a diagram is usually a really good idea for these. This is not a very good diagram, but it'll probably work. Here's the focal point. The focal length is 12 centimeters, and the object is located 8 centimeters from the mirror. So here's my object. It's inside the focal length. What can we expect for the image? Well, that was the first case that we tried. That was where my nose was right up against the mirror, and you saw, or where that ball was right up, pressed up against the mirror, and you can see that the image was upright, and it was virtual. The array diagrams show that it was virtual. So we expect an upright, virtual, and in fact magnified or enlarged. Enlarged is just another way of saying magnified. we expect that image to be upright, virtual, and enlarged. Let's actually just do the quick ray diagram to make sure we're not being... so there's one ray. Here's another one. There's a center of curvature. It's not very accurate. So if I draw the line from the center of curvature through the tip of this object, it's going to hit about here, come right back on itself, and head out for Timbuktu. These three appear to be converging somewhere over here. So that looks like we had to extend the rays to get the image. So it must be virtual. It's upright, and it definitely looks enlarged here. Let's take a look. We know F. We know the object distance, 8 centimeters. So what we're going to try to do is to solve for the image distance. I want dI. So I'm going to subtract 1 over dO from both sides of this equation. And that gives me 1 over dI is 1 over F minus 1 over dO. Plug in the numbers. That's minus 1 over 20, do the algebra, minus 1 over 24 centimeters. But remember, just like we did with resistors and capacitors with that inverted relationships, that's not your answer. Your answer is 1 over that. So 1 over dI equals minus 1 over 24 centimeters. That's why I always carry the units along. Otherwise, I'm just going to write down that as dI, and I'll be wrong. But the units are in the denominator, so that's your clue that you better invert it. So dI is minus 24 centimeters. Well, does that square with our diagram here? Well, we had 8 centimeters, 12 centimeters, so this is about 12 centimeters, about 12 on the other side. It looks like it's more than 12, so, I mean, roughly, it's out there further than the focal length, and that's where the image is. So we get a negative number for dI. What does that tell us? If dI is positive, that means the image is real. But if dI is negative, it means that the image is over on the other side of the mirror, and the image must be virtual. So that minus sign gives you the information that the image is virtual. Let's also do the magnification. Magnification is the height of the image divided by the height of the object. And given the magnification equation, that's minus dI over dO. Well, we've got dI and we've got dO. Let's plug the numbers in. There's a minus sign. That's this minus sign. dI is minus 24 centimeters. What's dO? Well, dO is this 8 centimeters. Well, this minus sign kills this minus sign, and 24 divided by 8 is our old friend 3. So the magnification on this is 3 times magnification. Can you believe that the height of this image in this diagram we've got here, this height here, compared to the height of this object, that this might be about 3 times? And you say, yeah, it looks like 2 or 3 times as much. So the diagram we've drawn here squares with the math that we've done. The math, also the magnification ended up being a positive number, which is another indication that the image is upright, not inverted. Otherwise, we would have gotten a negative number for the magnification. That's how these go. An object is placed at the center of curvature of a concave spherical mirror. So that's this case where we have a mirror, focal point, center of curvature, and this is where my object is. And which of the following descriptions describes the image produced in this situation? We can do a quick and dirty graphical. Here's one ray. Here's another ray. And so where are these guys going to be? These guys cross right here. So it looks like we've got an image. In fact, I didn't draw that line very well. Should have been up here more. Looks like we've got an image that's at the same spot as the object. And it looks, by the symmetry of this arrangement, it looks to be as far below the axis as the object is above the axis. And in fact, that's exactly what we saw in the video where I was backing away from the mirror. When I got to that center of curvature, we had an image that was the same size as the object, but inverted. And so inverted is certainly true. Is the image real? Do these rays that come to this point actually pass through that point? You bet they do. And the other hint of that is that you don't have to do anything behind the mirror. Everything's in front of the mirror. So it's going to be a real image, and it's unmagnified. So that one goes. You can actually plug in and do this with equations as well, that the 1 over f is 1 over d naught plus 1 over di. And if the object distance, so f is this distance, it's the focal length, little f. What's the object distance? Well, that's from here to here. So what's that distance compared to f? Well, it's just twice f. And in fact, the object distance is the radius of curvature. So given that, we can actually solve this equation. So this is 2f. We can solve this like we did before. If I want to solve this for 1 over di, it's 1 over f minus 1 over d naught. That's 1 over f minus 1 over d naught is 2f. We have to get a common denominator here. This one's 2f, this one's f, so I'm going to need to multiply and divide this fraction by 2 in order to get a common denominator. So then we have 2 minus 1 divided by 2f. That's just 1 over 2f. And that says that 1 over di equals 1 over 2f. What does that say di is? And do is also 2f. So they're both in the same spot. The image is at the same place that the object is. And because the magnification is minus di over d naught, di and d naught are both 2f, we just get minus 1 for the magnification. So that is the magnification in this particular case. Another example, convex mirror. Let's do an example with that. Is used to reflect light from an object placed 66 centimeters in front of the mirror. Remember, the convex mirror is the easy one. All right, the focal length is minus 46. And you say, well, there must be a typo here. The focal length can't be negative. And I say, yes, it can. Remember, the focal length of a convex mirror is a negative number. So if this is the focal length, the focal point, the distance, or the negative of the distance between the mirror and the focal point is the focal length. And we're placing an object 66 centimeters. So if this is the symmetric focal point here, we're actually out here a little bit further away than the focal point. 66 versus 46. So where's the image going to be? So there's a ray, bounces off as if it were coming from the focal point here, Here's another easy ray to draw. And do these two rays, 1 and 2, appear to be converging or diverging? Well, they're definitely diverging. And we're going to look for an image right here. The image is going to be virtual, reduced, and upright. So let's see if the math confirms that. We end up, just do the math in the same way we've been doing the math before. Find the image distance, it's minus 27 centimeters. We say, oh, darn it, I must have made a mistake. The image distance is negative. And I say, not a mistake. It gives you the information that this image is virtual. That minus sign says the image is virtual. Perfect. Plugging in for the magnification, the same thing we did before. Magnification is 0.41. What does that say? Well, what matters for the magnification is whether it's bigger or less than 1. In a telescope, you talk about 100 times magnification or whatever. That means it's magnified. If the magnification is 1, it's not magnified at all. It's unmagnified. If the magnification is 0.41, it's less than 1. That means it's reduced. And upright or inverted, the image is actually upright. Because this is a positive number here for the magnification, that tells you that the image is upright. Because the height of the image, this hi here, must be positive. Hi divided by h naught. Remember, the magnification is hi over h naught. And it's also equal to this. But in thinking about the definition of magnification, it's the height of the image over the height of the object. And the magnification is positive. The object is object height, h naught, is a positive number. And therefore, the height of the image must also be positive. That's everything to say about that one. Which of the following statements concerning a convex mirror is true? Such mirrors are always a portion of a large sphere. Actually, they can be parabolic. I mean, most of everything we're talking about here is spherical. The image formed by the mirror is sometimes a real image. That's true. In fact, it's never true. It's never true. It's always going to be a virtual image behind the mirror. The image will be larger than the one produced by a plane mirror in its place. Well, that's not true. It's actually going to be reduced. They're always reduced. The image will be closer to the mirror than the one produced by a plane mirror in its place. This is the one that's actually true, and this is an important one. Notice that this image, okay, so here's the image distance, 27 centimeters. So that's this distance between the image and the mirror. That distance is less than the object distance. And when the image distance is less than when the absolute value of the image distance is less than the object distance, then the image is going to be reduced. You can take that one to the bank, because if the image distance, this di here, is less than d naught, then this number is going to be less than 1. The absolute value of this number would be less than 1. It might be positive or negative, but we're just talking about the absolute value. Then that says that the image height is less than the object height. So anytime, here, let me just write it one more time. The absolute value of the magnification is absolute value of hi over h naught, which is equal to the absolute value of di or d naught. What that says, sorry, is that if the image is reduced, then the absolute value of hi over h naught would be less than 1. If that's true, then the image is going to be closer to the mirror than the object. So let me just state that. If the image is reduced, and this is true for convex, concave, whatever, then the image will be closer to the mirror than the object. We're not worried about which side of the mirror right now. We're just talking about how close it is to the mirror. And if it's reduced, then the image will be closer to the mirror than the object.